Now we shall prove Fermat's theorem on sums of two squares. Recall the statement. Fermat's theorem on sums of two squares says prime number p is the sum of two squares if and only if p is 2 or p is congruent to 1 modulo 4. There are 3 steps in the proof. This is the first step of the proof. We may assume p is an odd prime number because theorem is obvious when p is 2. Assume that p is the sum of two squares. We write p is equal to the square of x plus the square of y for some x and y. Here is a table of the square of x modulo 4. You can confirm that the square of x is congruent to 0 or 1 modulo 4. The same is true for the square of y modulo 4. Combining these two tables, we see that the square of x plus the square of y is congruent to 0 or 1 or 2 modulo 4. It is not congruent to 3 modulo 4. Since p is an odd prime number, we conclude that p must be congruent to 1 modulo 4. We shall prove the converse direction. Assume that a prime number p is congruent to 1 modulo 4. We put p is equal to 4n plus 1. Let a be the factorial of 2n. Then, by Wilson's theorem, minus 1 is congruent to the factorial of p minus 1. It is the product of all the integers from 1 to 4n. Since p is equal to 4n plus 1, 2n plus k is congruent to the minus of 2n plus 1 minus k. Therefore, the factorial of p minus 1 is congruent to the factorial of 2n times the factorial of 2n times minus 1 to the 2n, which is congruent to the square of a. We conclude that the square of a is congruent to minus 1 modulo p. This is the last step. Recall that the square of a is congruent to -1 modulo p. Consider ab plus c modulo p. For non-negative integers b and c less than the square root of p. Since the number of such pairs BC is greater than P, AB plus C is congruent to AD plus E modulo P for some different pairs BC and DE. Now we put x is C minus E and y is D minus B. Then x is congruent to AY modulo P. Since the square of A is congruent to -1, this implies the square of x is congruent to the square of A times the square of y, which is congruent to the minus of the square of y. Therefore, the square of x plus the square of y is congruent to 0. Namely, the square of x plus the square of y is divisible by p. But it is less than 2 times p by construction. Therefore, we finally conclude that the square of x plus the square of y must be equal to p. Now the proof of Fermat's theorem on sums of two squares is complete. Let's summarize the topics we learned this week. We learned there are laws of prime numbers called reciprocity laws. Fermat's theorem of sums of two squares is the first non-trivial example of such laws. Then we studied basics on modular arithmetic, which is a convenient tool to calculate remainders of integers. Then we proved 3 important theorems in modular arithmetic: Fermat's Retier theorem, Wilson's theorem, and Lagrange's theorem. Finally, combining these theorems, we prove Fermat's theorem of sums of two squares. Next week, we will learn more general reciprocity laws, the quadratic reciprocity laws of Gauss, and its generalizations. It is an amazing fact that there are so many interesting laws and prime numbers obey all of them. Some of laws are yet to be discovered. Let's discover hidden laws of prime numbers. See you next week.